Our next speaker will be Professor Darwin G. Caldwell from the Italian Institute of Technology. His title of the talk is Robotics for Healthcare, Construction, and Agriculture. I will briefly introduce our invited speaker, Professor Caldwell. He is founding director of the Italian Institute of Technology in Genoa, Italy, and director of the Department of Advanced Robotics at IIT. Professor Caldwell was a pioneer in the development of core technologies in compliant and variable impedance actuation, soft and human-friendly robotics, and the creation of softer, safer robots that draw on developments in materials, mechanisms, sensing, actuation, and software. These developments have been fundamental to advances in humanoids, quadrupedal robots, and medical robots. Key robots developed by his team include the very famous ISRIAH, a child-sized humanoid robot capable of crawling, grasping objects, and interacting with people; Command, a controllably compliant humanoid designed to safely interact with people and have more natural locomotion; Walkman, a 1.85 meter tall, 120 kg humanoid that competed in the DARPA Robotics Challenge; the HYQ series of high-performance hydraulic quadrupedal robots; and the Pholas Centauro, a humanoid robot symbiotic system capable of robust locomotion and dexterous manipulation in rough terrain and harsh environments. Professor Caldwell is honorary professor at the universities of Manchester, Sheffield, Bangor, and King's College London in the UK, and Tianjin University in China. He has published over 700 papers, has over 20 patents, and has received over 50 awards and nominations at international conferences and events. In 2015, he was elected a Fellow of the Royal Society, Royal Academy of Engineering for his outstanding contribution to robotic systems, their mechanisms, electronics, and control. In 2022, he was elected a Fellow of the IEEE for contributions to actuator technology, leg systems, and soft human-friendly robotics. It is our honor to have Professor Caldwell among us for his today's talk on robotics for healthcare, construction, and agriculture. Professor Caldwell, please.
Thank you very much for that kind introduction. Can you hear me okay, and can you see my screen?
Yes, we can hear you as well as the screen. Thank you.
Great, thank you very much. Thank you for the very kind invitation, and thank you for the opportunity to be here virtually. As was mentioned, yes, I'm going to talk a little bit about robots for healthcare, construction, and agriculture, because I think that's the main theme of the symposium. Particularly, I will focus on our healthcare robots, but it was suggested to me that I should probably give it a little bit of an overview of all the work that we do at IIT. IIT is the Italian Institute of Technology in this instance, not the Indian Institute of Technology. So I'll give really a broad overview of the robotics that we've actually been doing at the Italian Institute of Technology. So just to set a little bit of background, this is essentially what we can actually see. This is what we can actually see within the activities of the Advanced Robotics Department at IIT. IIT was founded in 2006, so it's about 15, 16 years. It's 16 years old in July of this year. And I was the founding director, one of the founding directors, and particularly I was responsible for the foundation of the Advanced Robotics Department. And if we actually look here, we can see the areas that the Advanced Robotics Department actually covers. So it covers a very wide range of activities. So we have on the one side, on the left-hand side here, we have surgical robotics, wearable technology, exoskeletons, augmented reality, tactile sensing. And it's in this area that I will focus a little bit in this particular presentation. We have at the core of all our work mechatronic systems, the mechanism design, actuation, sensors, control, and dynamics. On the right-hand side, we can see some of the activities that were already mentioned, the work that we actually do on humanoid technologies. So we have various different types of humanoids, bipeds, quadrupeds, four-legged robots. We have Centaur. Centaur is a robot which is half designed to be like an animal, like a horse, and half like a human. So you have an upper body like a human, a lower body like an animal. We develop these systems in terms of electric actuation, in terms of hydraulic actuation. We want to do things such as whole body planning, and we develop them into a number of different types of technologies. So we have humanoid robots such as the ICAB mentioned, the Coma, the Walkman, the Centauro, and we have quadrupeds such as HiQ, HiQ2, HiQ Rail. These activities on the right-hand side are focused within a series of different labs on humanoids, on dynamic-legged systems, which is quadrupeds, on soft robots to assist humans, so that's for human interaction. Again, human-robot interaction and interfaces, very much focused, but with a little bit more of an industrial focus rather than just an aspect on the integration. And then finally, we have rehabilitation robotics. This is the area I will just go through very quickly. What I want to focus on is our more recent work. So the advanced industrial automation, one project that we've actually done there, which is a very large construction project, which was on a bridge, and then focused primarily on the work in our biomedical robotics lab, which is our healthcare activities, and in our exoskeletons lab, where we actually develop exoskeletons again for industrial operations, which could be into construction. And then a little bit, we will talk on some work in the ISRIAH lab. ISRIAH lab is active perception, but we do some work here on precision agriculture. So it'll be a very, very fast tour across all of these types of activities. So just to give you a little bit of a history, as was originally mentioned, I said the IIT was created in 2006. After the ICAB, which was built in a project prior to the setup of the IIT, the first robot we built was what we called the CCUB. The CCUB was a compliant. So traditionally, humanoids and humanoid-type robots have always been very rigid. In fact, all industrial robots are very rigid. They're not designed for interaction with humans. And so the CCUB was designed as a compliant robot. You could actually physically easily interact with this. It was designed to have an ability to go between being soft and being very, very stiff. And so you could modulate the stiffness of the actuators in a way which was reminiscent of what you could do in humans. We then focused that into a robot called Coma, which is a very small humanoid. So it's about 1.20 meters tall. Doesn't actually have a head, but it's 1.20 meters tall. This was built in 2012. Then we focused that into the Walkman robot, and there's two versions of this, a 2015 version and 2018. This was a very large robot. This robot was 1.80 meters, 1.90 meters tall. The first version weighed 120 kilos, and that competed in the DARPA challenge. The second version, the 2018 version, weighed about 90 kilos. Had the same power as the original version, but was a much lighter structure, so it's construction. And we then focused that into what we call the Centauro. And so what you can see here is 4 legs, actually wheels, as well as walking legs, 2 arms, and a head. And this then flows back in a negative direction across the HiQ series of robots. HiQ stands for hydraulic quadruped. And so the first HiQ robot was built in 2010. A second version of the HiQ 2 Max was built in 2015, and in actual fact, there's a third version called HiQ Rail, which was built in about 2018, 2019. So these are some of the actual humanoids and quadruped platforms that we developed. Very, very large systems. I mean, these take thousands and thousands of hours. It's like developing a whole car or something like this. So it's very, very complex systems, many people involved in the actual operations. And so this is just to actually show you a little bit of what some of these works. And so some of these go back for maybe 10, 11, 12 years. And here we can actually see the top left. This is the C Cub. And then most of the other robots here are versions of the Command robot. And so you can see in the middle how easy it is to physically interact. You wouldn't do this with a normal type of industrial robot. And you can see how the compliance can actually be regulated. And this, we believed at the time, was a very important aspect of robots that you know, maybe 10, 15, well, 20 years ago, certainly, to have robots that interacted with people was very unusual. And to be able to have a humanoid robot that did this was totally beyond the bounds of expectation. And so what we were wanting to do was to develop these robots that would actually be safe and actually perform better next to humans. And so these are where the ideas for the Coman and the series came from. Again, some slightly different versions of this. So you can actually see the robot is very tolerant of impacts. You can push the robot very effectively. It's able to step over large objects. You can see the interactions, completely unplanned interactions, and the robot is able to deal with this in the same way that a human would be able to deal if someone was pushing the human around. Then we had some larger. So this is the Centaur robot. The Centaur, both the Centaur and the HiQ were invited to the Mars events. So every year prior to the pandemic, Jeff Bezos used to hold a special event where they'd invite a small selection, 4 robots from around the world to the event. At the first Mars, which was in 2016, 2017, the HiQ was invited. In the last one before the pandemic, 2019, we actually had the Centaur. So of the 16 robots that have been invited, 2 of those robots have actually come from IIT. And here we can see this is the Walkman. This is the Walkman version 2. And this is actually another robot which we developed subsequent to this, called Kujimon robot, which is again a slightly tall but slightly lighter robot. So we were aiming for a more human-sized and human weight robot. The original version of Walkman, as I said, was 120 kilos. Here we can actually see the HiQ stepping across, but I have some slightly better videos of that in the next slide. And so again, here we can actually see the HiQ, and we know that now many of these things can actually be done with various different types of robots, the Spot robot, Unitree, etc. But you have to remember some of this work was done 10 years ago. But what we can actually see is robot very capable of adapting to different environments, being able to climb up over a series of steps or a series of pallets. Here we can actually see a number of different surfaces it can climb onto, up different surfaces. In the bottom left, in the bottom left, you will actually see it stepping across. Now, this is quite a dangerous thing for a quadruped. If its leg falls into those gaps, it will actually break the leg. What this robot is actually doing is able to spot where the gaps are and able to adjust. In the bottom right, you can actually see it stepping across quite large step surfaces. Again, back to the bottom left, what we can see is we can dynamic. So the person will pull on the reins and deliberately try to pull the robot across the gap. And it has to step onto the steps and manage not to break a leg. In the bottom right, it's actually planning very specific leg motions, so front and back legs, to where you can actually put its feet so it can step across stepping stones. So if it is going across a river or something similar to this, able to plan those types of motions. And again, this is just showing the top robot. The top robot is the HiQ. So this is HiQ Real. This is the most recent one. This is just to actually show how strong this robot is. And so here we can actually see the robot pulling a plane. So this small robot will actually pull a plane. On the bottom, top right, you see the Centauro robot outside. So these robots are all fully autonomous. They will actually operate away from environment. They don't need any cables. They have their own onboard power supply. The bottom left, this was the original Walkman robot. So you can see the robot sets off and pulls the plane. So it's a small private jet. So it's quite a large surface that we actually have. Here we can see the robot, and the bottom, top right, you see the robot. It's lifting a brick. I think it's 7-8 kilos. This particular brick, as it turns around, it actually says the weight on the brick, and we can actually see what sort of size that is. And then you have the Walkman at the bottom. Okay, that was to give you a little background on perhaps some of the robots that IIT is best known for, which is its humanoids and quadrupeds. But for this particular presentation, I wanted to focus on our work on healthcare, because I think that fits best with what the theme of the workshop. And so what we're actually working on is our biomedical robotics lab. And within our biomedical lab, what we want to do is to develop assistive technologies to augment the performance of the surgeon. So we're not about developing robots which do surgery. What we want to do is to develop robots and robot technology which will actually assist the surgeons so they can do a better job. We want to have a human-centric robot technologies. We want to have a direct impact on health and well-being of people, of the patients and of the surgeons. We want to have intelligent interfaces and intelligent mechanisms. And so one of the first areas that we focused on was what we call computer-assisted laser microsurgery. And this is the laser setup. So what you traditionally have is you would have a surgeon. This isn't actually a surgeon. This is Leonardo D'Amatos, who is head of the biomedical robotics lab in my department. And so he's actually doing this system, but he's using the very typical system that you could actually have. So you would have the surgeon. They would operate through a microscope, a traditional type of microscope. Their left hand would operate a series of forceps, but normally with the right hand, they would use that to guide a small joystick, a very traditional old joystick that was used on a gaming system to actually control a laser pointer. And what we've actually developed within the labs, the biomedical robotics labs, is we developed this CAM system. This is a patented system. We actually have a series of mechanisms to control the actions of the laser. So it's a fully automated laser system. It's a patented system that we have patented worldwide. And what this can actually do is, using the tablet you can see here on the right-hand side, so the surgeon now, instead of using this old-fashioned joystick, actually essentially draws. They use a system which is very like using a coloring system, like a writing system, like a drawing system. And we can see here in the bottom right, the area in red, the surgeon will actually outline that particular area. So you'll see he draws around this, highlights it, and now he wants to do a process called ablation. So essentially ablation is to rub the surface away. And what you can see here is the laser scanning backwards and forwards very, very rapidly across that surface, essentially rubbing that surface away. It's actually vaporizing the surface. In the other videos, which unfortunately are not playing, what we can do is we can create safety regions. So what we would actually have happened in the video here, you can actually outline this area. So you want to cut the tissue here, you want to cut the tissue here, but in the middle, you want to outline this area and the laser would turn off. And the moment that we move into that safety area, the laser would turn off. And so we've actually taken this particular system and done a number of trials. So we're actually in clinical and preclinical trials at this moment in time. In the top left, what you can actually see here is we're very fortunate. A few years ago, 150 top international surgeons visited Genoa, where IIT is based, and they were able to trial this system. And so you can actually see the surgeons actually trialing this system at this moment in time. This is with an animal larynx. So it's just for the demonstration, was on an animal larynx. And what we actually had was the traditional tablet that we used, the microscopes, and you can, if you actually look at some stages, you may even see a small puff of smoke as the tissue is vaporized. On the right-hand side, let's play this again. So on the right-hand side, this was a demonstration, a live demonstration, which actually was done by one of the world's top surgeons at a conference in Rimini in the east of Italy. And what you can actually have is this is set up with a cadaver. And here, instead of using the microscopes used before, they're actually using a stereo screen, and you can actually see it when you put one of the lenses of the glasses. You can see it goes from a stereo, a blurred stereo, which you can see with the camera. But the surgeon, we actually just go back and do this again. So you see the surgeon now is wearing a series of glasses, so he's not looking at the microscope anymore. He looks at the display. All of the other people in the operating theater are able to do the same thing. So everybody's able to see this. These are cadaver experiments, as I've done live. We used the CAM system developed at IIT and a commercial system by Storz, which is the Viton 3D exoscope. So this is the concept of what we're wanting to move towards. So what we actually have now is the surgeon. This is again a surgeon from a hospital in Milan. And so the surgeon's using the tablet, but he also now has replaced the forceps with a haptic device. And so this is a 6 degree of freedom haptic device where you can manipulate the tissue. On the right-hand side, you can see a robot being manipulated, the tissue being vaporized. And this is done by the surgeon operating the haptic device. Controls the laser with this, controls the physical manipulation of the robot with the left hand. And he has a stereo image, which shows the real stereo image, but we can also add augmented reality systems on top of this. So we can add additional information to help the surgeon to provide information on the temperature. So as the laser actually vaporizes the tissue, it creates an increase in the tissue temperature. And so we're able to do this. So we have a variety of different systems in here. So we have a head-mounted display, virtual microscope, which is what we call it. We have 3D imaging. We have the microscope itself, which now uses stereo cameras. We have the laser beam, which is focused onto that, the haptic display, and we close this particular loop so the surgeon is completely in control of all aspects of this. And we then move further than this. So about 3 years with this back in 2019. Doesn't feel so long ago, but actually looking back, it's quite a long time. So back in 2019, we were fortunate enough to be able to do possibly the world's first live demonstration of a 5G telesurgery. So this was actually done between Vodafone Village. Vodafone's the telephone network providers. So Vodafone have a large facility in the center of Milan, in the north of Italy. And so the surgeon was actually in this site, actually in a large hall on site in the Vodafone Village. And then we had a cadaver that was actually at San Raffaele Hospital, which is 15 to 20 kilometers away. And so we were able to do the operations. And the type of operation we had here was we had the tablet that was mentioned before, the haptic device mentioned before, the 3D display, webcam. So this was all on the user side. 5G communication to the patient side, where we had the CAM system, the computer-aided laser microsurgery. We had a Franco robot. We had the Karl Storz Viton 3D imaging system, and then external cameras. And then we send this image back over a 5D system. And because it's a 5G system, the latency is very, very low. The image quality is very, very high. And we actually did this in a live demonstration. And so this is in front of an audience of about 200 people. So here again, you can see the surgeon. This is Leonardo explaining what actually goes on. And in the next one, what we can see here, if you hear a slight buzzing, the slight buzzing is actually the noise of the laser. And you can see the tissue being ablated. This is in the surgeon site. So this was in the morning. We were doing some tissue. We were doing this on just some animal tissue. In the afternoon, we actually did it on a cadaver. I want to show you the cadaver experiments. This is the experiment. So this is actually the external. When you actually see the internal, that's on a cadaver. Here you see the surgeon. So this is the image you saw just at the start with the tissue on the vocal cords, manipulating the robot, controlling the laser, and then an external display on the room. The imaging here, this is actually just showing you details of the actual latency. which from an engineering perspective, you can see it's very small, typically under about 80, 90 milliseconds of latency, which means the surgeons are able to perform the surgery very, very rapidly. Okay, I'll move along very quickly. This is another type of a system we're actually doing. What we developed here was a biomedical impedance sensor. So what we were able to do was to actually measure the impedance of tissue. We could measure its magnitude, its resistance, we could measure the phase change. And every type of tissue has a different magnitude, different phase change. So here we can actually see the magnitude for fatty tissue, we can see the magnitude for muscle, we can see the magnitude for cartilage, for different types of materials. And you can see if you look on here when the person's actually touching, so they use the probe, and you'll see displayed on the surface, it will say that this is muscle tissue. And so we can identify every different type of tissue by its impedance characteristics. So what this allows us to do is real-time tissue identification characterization. We believe we can use this for cancer detection. This is one of the things we're trialing at this moment in time. We can also do it for catheterization and for drug development. So one of the first things that we've actually been doing, so if you're a little squeamish, you can look away at this point, is we want to do what's known as peripheral intravenous catheterization, right? And this is essentially where you put a line, you put a needle into someone's hand. It's a very common procedure. 5 billion of these procedures are performed every year. Often with difficult patients. So if you have elderly patients, if you have people with veins which are compromised, this can be difficult. It's also very common, very difficult thing to do in newborn babies. And often you try to put a line in with babies that have been born and have some sort of condition. And so there's 5 billion of these. Often takes 3 or more attempts to actually do this, which can be very, very painful, very distressing. One of the issues that can happen, so there's 2 issues that are common. The first, that the needle will go through the vein, out the other side, and the material is actually injected into the tissue, but having got into the tissue around, and you can see it create very, very nasty side effects. These side effects are not just painful, sometimes they can actually be life-threatening. And so you can actually see this. And so what you want to do is you want to ensure that the needle goes into the vein and no further. And using this bioimpedance, what we can actually do is we can actually measure the impedance of blood. So the moment the needle goes into the vein, we can tell the person who's doing the injection that they are in the blood vessel. And so we've developed a series of different systems. These are the SVEI, the Cathbot. There is another version, Cathbot Pro, but that's a version we're working with a company, and I can't actually show you that. So what we actually want to do is we want to do the needle insertion. If you watch here, there'll be a green light comes on in a second. Green light comes on. This means it's detected blood. So this was actually done and you can detect the blood. The information you can see down here, this is the success rate with people who have never tried this system before. So someone who has never done a needle puncture before, using this system is 86% success rate on their first trial, right? If you remember, I said that often professionals, people have years and years of training, will take 3 attempts to actually do this. You will realize that this system is very, very effective because with no training, you get nearly 90% success. But we move beyond that. We now have this Cathbot, and with the Cathbot, not only does it detect the presence of the blood, it physically removes the needle. So there's actually a needle retraction, and the system we have beyond that actually not as well as doing that, doesn't actually need the manual insertion. So if you actually look here, it's synthetic, but you will actually see a small pulsing of blood. You might have seen a small red pulsing here, and this is actually showing that the blood is actually present in this dummy arm. Another system that we want to use is what we call for surgical guidance. This is essentially a GPS. So whenever the surgeon's actually inside the abdomen, it can be very difficult to actually tell exactly where they are. And so what we've actually done is created this 3D tracker that essentially is able to tell where the surgeon is inside the abdomen, be able to go close to the liver, close to the kidneys, etc., so that they know exactly where this is. And we can then map that to preoperative imaging, such as CT, MRI, etc. So we can actually add this. But we've gone further with this. And so what we've actually done is, in this instance, we've actually linked it together with the Da Vinci system. So we have a Da Vinci technical kit. And what we're able to do here is we're able to use a series of probes to, as well as use the imaging system, be able to use the bioimpedance to be able to detect the tissue. So when we touch the tissue, the video, so when it touches the tissue, it will actually come up here just where it says unknown. It will touch a piece of tissue and it will tell the surgeon exactly which part of that tissue it's actually touching. So it just comes in here, measures this and telling you it's touching the lung. So it's able to classify the lung as well as everything else. And we can move further. What we can actually do here is, if there was some sort of inclusion, if there was some sort of tumor present in this, we are able to move around, and we have already done tests which actually show that we can detect the presence of different materials within this. We now want to move this forward so that we can do real clinical trials to be able to see if it's possible. This is simply using this probe, we will be able to detect the presence of malignant tissue and healthy tissue and be able to tell the difference in that, and then subsequently be able to move forward and do different types of operations. It's also valuable to the surgeon because this will actually define the boundaries of a some sort of malignant tissue. So you can actually say that the tissue here is healthy, the tissue here is malignant. But what you want to do is to find out exactly where the edges are, because you want to remove all of the bad tissue and nothing else. You don't want to remove any good tissue. So now I go forward. We do many, many, many different types of surgery, but just in the just to try and observe the time, I want to move forward. So each of these slides shows 4 different types of surgical procedure. So in the top system, what we're actually looking at is when we do the laser surgery, we use this laser, it essentially vaporizes the tissue. When it vaporizes the tissue, everything becomes very hot. You can essentially cook the tissue, which is a very bad thing to actually be doing. So what you want to do is to remove the tissue with the minimum amount of scarring. And so we developed an AI-based system to be able to work out the temperature, and we can feed this back to the surgeon. In the head-mounted display, we can feed this back. And so if you actually look here, you'll see a color probing, and it's actually showing the surgeon the temperature of the tissue, and we can either display the temperature of the tissue, or we can physically stop. In the bottom, we can use these same lasers to remove tattoos. So tattoos are quite often people get tattoos, and then many years later, they'll decide this was a really bad thing to do. And so what we have is the lasers, and we can actually use the lasers to automatically remove the tattoos. In the top right, what we wanted to do was to take it. The current system, we use a free beam laser, so the laser is open. But now what we want to do is develop this into an endoscopic laser so that we can actually do operations in the abdomen or inside the body and be able to twist and turn. We use brain-computer interfaces. So this is a slightly different application. This is for people with motor neuron, ALS. And what we want to be able to do is the person can wear a cap. They can measure their actual brain signals, and we can use this to control a mobile platform. This is some work. This was actually demonstrated with an ALS patient. The images you see here are from the Vatican in Rome. And the robot was able to go around, had access to the Vatican, was able to go into the Sistine Chapel and some specialized areas. And the person with ALS was able to actually to navigate around this environment that they would have been impossible. They were completely bedridden. They couldn't move. They had no motion at all. The only motion they had was the ability to move their eyes. They lost all limb control. Breathing even was a difficulty for them, but they were still able to control this robot. Various different types. So I said about the endoscopic laser. I wanted to be able to put it into a fiber. And so what we're actually doing is when you put it into a fiber, it's very difficult to control the laser. But what we've actually done here is we've put magnetic coupling in here, and we are able to physically move this laser inside a fiber optic. When you do that, it can be very difficult. What you actually have to do is you have to create this a magnetic CO2 laser. And so you actually do these motions, and this particular piece of work is actually looking at how you can actually create the system. And so this is a fiber optic laser, just cutting a piece of plaster that we often use for tests to see how effective it is. With these lasers, It's very important to be able to focus because you don't have the normal focusing mechanism. And so we developed a specialized focusing mechanism based on hydrogels that was able to do this. When we have the imaging that we have this is in the throat, so this is imaging taken from the throat, and what you can actually see here is a tumor, and we want to identify this, but sometimes it's difficult to actually tell. So this is clearly tissue which has been compromised. This is healthy tissue, but the boundaries are very difficult to actually do. And so what we've done is what we call is endoscopic tissue analysis, and so by imaging this under a variety of different imaging systems, different frequencies of lighting, we can actually tell the difference between the healthy tissue and the malignant tissue. We can use similar imaging systems to be able to track particular surfaces. So if there's a particular vessel that was it was critical that we didn't damage this, we can actually highlight this. This is not so important for a very experienced surgeon, but for a new surgeon who's doing this for the first time, it's very important that you can highlight these things and prevent them from making some sort of mistake that could be very costly, both in time, but also potentially also could lead to some very bad outcomes. We do automatic organ recognition. The versions we do here, we do a lot of work with pediatric surgery. And so these are for neonate. These are for babies who are within days to a few weeks of being born. And what we want to be able to do is to do surgery here, particularly neurosurgery, so to be able to operate on the brain. And you can see this is going to be very, very small. Typically, it's the size of the brain would be the size of an orange or something like this. We want to be able to do the vessels. In this, again, this is for unborns. And so a condition that happens quite often not quite often, occasionally, with twins is that we have two twins in the womb, but one twin will receive the majority of the blood supply and food supply. The other essentially gets nothing. And so one twin is very small, one twin is very large. What you want to do in this instance is to be able to cut the blood supply from one to the other, because essentially the blood from one is going to the second one. And you want to be able to catheterize this so that they both grow in a healthy way. So we do some work on this. We do work on active constraints. We do vision-based fetal surgery, which again is an extension of what I showed before. Our emotional interfaces are for the ALS. So as well as being able to measure people's brain signals, we can also measure their emotions. We measure their heart, we measure their blood supply, we measure the sweat, etc. We can do computer vision liver grafting assessment. Sorry, I'm going very quickly at this moment in time because I'm pretty. In fact, I have a couple more slides. Do you want me to finish now because I'm a little over time?
Yep, about 4 minutes, Professor.
Okay, so the next bit I'll go through very extremely quickly just to show you some work that we're actually doing in musculoskeletal disorders. So these are the types of things that happen in a working environment, in the construction type environment, and even farming environments. And what you actually have is you're lifting things, you're moving things around. You could end up with a lot of damage to your back. And these are very, very common injuries. In fact, the most common reason for loss of injury at work is from these musculoskeletal disorders. Damage to the nerves, to the muscles, to the tendons, to the ligaments. Okay, it represents nearly 2/3 of all the reasons people are off work. Number of workers, this is just in the UK, so it's a relatively small country, over 500,000 people every year. The bottom figure is perhaps a little bit more indicative. So they reckon in the EU, somewhere over 250 billion euros of estimated cost due to loss from musculoskeletal disorders, 2% of GDP. There are many different things. One of the things people have suggested is building exoskeletons, but you need to be a little careful with exoskeletons because while exoskeletons potentially help, they also have certain difficulties. So here I just want to highlight some of the difficulties where in exoskeleton, you have to be careful about the discomfort on the skin. You have to be worried about increased stress due to the fact that you're working the exoskeleton as well as just your normal job. You have to have worried about collision because the exoskeleton is bigger than you would normally wear. It's heavier, so there's an increased cardiovascular load, etc. But what we've actually been doing is we've been developing a series of different exoskeletons, and they can be like passive, where there's just springs, or they can be active, or they can be a mixture. We focus on the active exoskeletons and the quasi-passive. So they have a mixture. They're not fully active, but not passive either. The structures can be rigid, they can be soft, like a piece of clothing. The ideal scenario probably is to be like clothing, because this is the easiest. You don't wear any external structures, but at this moment in time, the rigid structure is the most common. The soft exosuits, we actually do work on those. So here we can actually see a relatively simple system. This is a quasi-passive, and so what the person actually do is they can put this on, and this provides a lot of support for their back. Using an exoskeleton. It's very flexible, as you can actually see in the left-hand side. It supports a weight. In this instance, it's supporting a relatively small weight of about 5 kilos, but we can actually change the actual loading on this, and we can actually change the levels of assistance, either passively or quasi-passively. But you can see it's a very flexible system and provides great support for the back. We do these types of things. This is a quasi-passive, and so what we've actually done is we put very soft actuators onto the joints. And so when the person sits down and they stretch the joints, they actually put an elastic energy in there. And then when they need to sit up, that is refed back to the person. So during that sitting motion, you store energy and then you release this energy. So it helps people to stand up. It helps people to do a variety of different actions. You can see it's easily built into textiles. It's not the most pretty at this moment in time, but it can be potentially very effective in the long term. We have here, this is some work for space, because astronauts actually lose a lot of muscle mass. And so this is a suggestion of a textile system that could be used by astronauts. Here we have a variety of different exoskeletons. These are the rigid exoskeletons for the trunk, for the bottom of the back, for the shoulder, for the elbow. Here we can actually see some examples. So this is used in a factory where they handle food. This is in the deconstruction of cars. This is a system that actually works onto the shoulders. This was at the local airport being used to actually assist people who were lifting heavy loads. So these are suitcases, which are typically 20, 25, 30 kilograms. Here you can actually see this particular system. This is for the shoulder. And this was done in a local garage where the person was able to go out and do car maintenance. And so work above their heads without any restrictions to their shoulders, and actually offload much of the loading that you'd have had if you were working above your head. Okay, just very quickly on construction. In Genoa, about 3 years ago, unfortunately, one of the bridges collapsed. Many people were actually killed, over 50 people killed. Since then, they've built a new bridge. And on the new bridge, they approached us and asked us about putting robots onto the bridge to actually do the maintenance and inspection on this particular bridge. And so here you can actually see, so the bottom just shows simulations of an inspection system underneath. This is the video you see at the top was showing a cleaning system for the solar panels along the side. And so these are robotic solar panels. So they are able to do the inspection. This is the underbridge inspection. So there's a series of cameras built into this. It will move backwards and forwards. The bridge is, I think, about 1 kilometer long. And so it goes backwards and forwards during the course of the year, doing an inspection, building up plans, being able to work out that the bridge stays in good condition. And this is some agricultural. I haven't got much of the details. This is the agriculture. This is what we call winter vine pruning. And this just uses a mobile robot, but we actually put it onto one of our quadrupeds. And what actually happens is that it goes out into the fields and it prunes these vines. And so it uses a vision system to be able to identify. And we did some tests on this actually just about 3 weeks ago, because it's the end of the winter vine pruning season. And there's only certain times of the year you can actually do this. So we do the lab tests and then move on to real tests. I'll finish. These are just showing some of the people. There are many. There's over 150 people working in various different aspects. So these are from the exoskeleton lab, the biomedical lab, but there's many, many other labs, as you can actually see there. I'll finish because I'm a little over time. Thank you very much.
Thank you, Professor Caldwell. That was an excellent and awesome overview of the works in the field of robotics at IIT. may I just ask the audience for a few quick questions? You can even chat it and I'll read it for Professor Caldwell.
Okay, can I ask?
Yeah, please go ahead.
Okay. This is Hiroaki Wangatsuma, the Kyushu Institute of Technology. I deeply impressed the work, so many the wide work and also the very advanced. So I'm interested in the medical surgical robot.
Yes.
What is the most difficult and challenging issue for the surgical robot? This is the visual processing or the mechanical control something?
In truth, the most difficult thing is dealing with the medical bureaucracy. This is actually why medical robots quite often take so long. So the technology we've been working on here has been in process, I guess, for about 6 to 8 years. And after about 2 years, we took it down to the local hospital and we showed it to the people in the local hospital. And they went, "This is great. Let's take it in next door into the operating theater and try this." And we went, no, we can't do this.
Okay.
Yeah. It has now taken us from year 2 to now in getting through because there are so many safety levels that you must put in there. It's not like your typical engineering. When you do a typical engineering project, you do it, you try, and you go out and you have an expectation that everything will be fine. But if it's 98% okay, you're not going to kill someone. Yeah. But when you actually do a medical system, you will kill. It must be 99.9, etc., etc. So this actually, in truth, is the hardest thing. But it depends what you're actually doing technically. What actually happened is that you can get the basic concept in place. And with many engineering things, what we actually do is we get the basic, and when it's 98% perfect, we write a paper and we publish it and everybody's very happy and goes, "This is great." And you go, that extra 2%, we will sort out the 2%. In medicine, you can't really do anything until you've got the full 100%. So everything has to be perfect before you can really talk about it, because if it's not perfect, it's not worth doing. So it's not just the technical process, it's actually that it's 100%. It's the reliability. If you work in industrial, I mean, a lot of the work we're talking about here is industrial. So the difference in going between the lab and industry, there's a step, and going to medicine is another step beyond that. You know, each time there's like, it's not just about technically, can I make it work? Can I make it work reliably? Then can I make it work with no failures?
Well, I totally agree with you. Thank you so much. Yes.
Thank you.
Good morning, Professor. My name is Kanaya. First of all, thank you for sharing the insights into the technological advancement in the healthcare domain. My question is also related to the 5G remote surgery that you have showcased. Suppose a surgeon wants to operate on a tumor inside a mouth, and he or she wants to feel the, let's say, softness or hardness, or maybe the texture of the tumor. So how can we provide technical assistance to that particular requirement from our end?
Okay, so it was something I didn't actually show here. We did a project once where what we actually were able to do was, by using the laser scan, so without physically touching the surface, we could then feed that back into the haptic device. So you saw the haptic device that I showed you. What we could actually do is we could feed that back. So normally when you do throat surgery, you really don't touch. You barely touch. You touch through the forceps, but forceps don't give you a great feel. But what we were able to do was scan the surface, and the surgeon could physically feel the surface. And initially, I was a little skeptical as to what would they want this, because they're not used to it. So surgeons often just want exactly what they are used to. But when it was fed back, a lot of them, not all of them, a lot of them said, "Yeah, this is really valuable. We actually want to do this." And by using things like the probes, we can actually potentially feedback textures that they cannot feel at this moment in time, because the surgeon cannot put his fingers inside your mouth and feel what this it's like. The actual vocal cords are 10 millimeters in length and even in more narrow, and they're at the back of your throat. It's impossible for the surgeon to feel. But the imaging that's there can actually image that, and then you can transfer that feeling back to a haptic device if you want to do it. It's not something we do often, but it is technically possible.
Thank you, sir.
And thank you, Professor Caldwell, once again for
Thank you.
your precious time. We appreciate it very much. And we might be having more questions and inquiry, which we will take up with you. Thank you so much.
Thank you.
Okay. So we will.
Good luck with the rest of your workshop. I'm sorry we can't all be there in person, but hopefully in the future.
Thank you. Thank you, Professor.
Thank you.